Welcome, everybody, to today's meeting of the CUNY Set Theory Seminar. We are very pleased to have James Holland, who is a current graduate student of Grigor Sargin at Rutgers University and the Polish Academy of Sciences. And he will speak to us about weak indestructibility and reflection. Okay, James, take it away.
All right, thanks for having me. So just to kind of give some motivation here. Forcing has brought about a lot of ambiguity about, say, what exists, right? And one reaction to that is to try and find axioms that tell us that we are in some sense immune to this technique of forcing, right? So there's lots of stuff about inner models with this property, right? So obviously L has this property, but also under some I guess anti-large cardinal assumptions. The core model below a wooden has this property. The Chang model under some large cardinal assumptions has its theory as invariant under forcing. So they have a lot of these sort of rigidity properties that tells us that they are really quite like concrete. Forcing axioms can also be seen as this sort of reaction to this ambiguity brought about by forcing. So a natural question that comes from this is, can we get large cardinals that are similarly immune to forcing? And we call such things, right, indestructible. So the answer is kind of no, trivially. For the most part, you can just collapse things down to be countable, right? But also sometimes yes. So the easiest example of this sort of thing is, right, when you have, say, a small poset, right, in which case the measures and extenders from V generate ones in the generic extension. So like measurable, strong cardinals, supercompacts, all that sort of stuff remain as such after we have this small forcing. But what about large forcings, right? Well, obviously those can like collapse cardinals down, but if we sort of avoid that, what's the situation, right? So what happens if we leave everything below kappa alone, or maybe everything up to kappa? And that's sort of a vague notion. There's a lot of ways to make that explicit, but the situation is a little more interesting. So here's a little bit of a history about some of the work in this area. So I believe it first kind of starts with Lever in his preparation to make a supercompact indestructible by less than kappa directed closed posets, right? Apter and Hankins then explore various ways of making all these supercompactor strongs indestructible, while there are a single supercompactor strong. Hankins explores ways of making things indestructible, destructible, and then resurrected. Apter and Sargin gets an equiconsistency with a kind of cardinal called a hyperstrong cardinal, with everything being weakly indestructible while there's a single strong. And then Apter later goes on to consider weak indestructibility for multiple strongs. Okay, but there's a sort of limit to the amount of indestructibility we can get in this sort of way. And really there's kind of a balance. So the specific theorem that we can adapt from what Apter and Hankins originally show is that if we have everything with its +2 strength indestructible by, say, co-enforcing, and kappa is strong, so everything below kappa is sort of indestructible, kappa is strong, and there's a sufficiently strong cardinal above kappa, then kappa does not have indestructible strength or supercompactness. Okay, so really the corollary to all of this is just to say that you can't have everything indestructible when there are two strong cardinals. Okay, and the proof of the theorem here is not too difficult, so we can actually go through that, right? So we're going to be adding a Cohen subset of kappa plus, and if kappa is still strong, what we can do is just consider this embedding from VA to MJ of A. That's sufficiently strong such that it realizes this lambda above kappa is still lambda +2 strong. Okay. Now, what's going to happen is that lambda's lambda +2 strength is destroyed by adding a Cohen subset of lambda plus. We'll be showing this, but for now, you can just kind of take it for granted. And as a result, lambda is also going to be destroyed in MJ of A by adding this Cohen subset. And so reflection down to V side tells us that there's going to be something less than kappa that has its +2 strength destroyed by coenforcing. And so back in V, we'll have destroyed delta's delta +2 strength by adding a coen subset of kappa plus and then of delta plus. But of course, adding a subset of kappa plus isn't going to change anything about delta +2 strength. So A isn't going to be destroying this. It's just going to be adding a subset of delta plus. Okay, so that's contradiction if we assume that everything below kappa was indestructible in this way. So all we really need to show is that lambda's lambda +2 strength was destroyed in VA by adding a subset of lambda plus. And for that, we use this result that if you are kappa plus delta strong in the cumulative hierarchy, then you're kappa plus delta, in the sense of delta cardinals after kappa, strong in the H hierarchy. So what I mean is that V and M will agree on H kappa plus delta. Okay, just a kind of small lemma that's used here. Okay, so suppose that we don't destroy lambda's lambda +2 strength after adding a coen subset of lambda plus. Okay, so that means that we have this sort of embedding here. So we might as well just assume that I was given by an extender, so we're closed under lambda sequences. By gap forcing, we're going to have a relatively small gap. So what we can do is we can restrict down to V to get this I restricted to V. That's still lambda +2 strong there. And so V and N will agree on what H lambda plus is. Now we can start examining what B is and where B is. So B is in H lambda plus in V A star B, as well as N A star I of B. But I of B comes from this forcing that's way too distributive. So it wasn't added by I of B, which means that it must have been in H lambda plus of N of A. So using some GCH to get some nice combinatorial principles, we can find a name for B in H lambda plus just of N. And then we use that gap forcing from before to tell us that that's the same as H lambda plus of V. And so we can just evaluate that name in VA to get that B should be in VA, which gives us a contradiction. Okay. So we can't have indestructibility for all degrees of strength when there are two strongs. So largely how research has progressed in this sort of area is to either consider indestructibility for everything, but just get a single strong or supercompact, or else get a lot of strong or supercompacts, but just ignore indestructibility for the small degrees. Okay, so my work is going to be looking at those small degrees of strength. So the main result is an equiconsistency, and we're going to be categorizing actually in the large cardinal hierarchy. So if we want alpha +1 many strong cardinals, and everything's +2 strength as weakly indestructible, and that's the same as having consistency strength-wise, alpha +1 many strong reflecting strongs. And I'll define what weak indestructibility and strong reflecting strongs are, but this is sort of the main result. And in fact, I think it's important to note that we can actually strengthen one, but it's still equiconsistent. So having that many strong cardinals with +3 strength as indestructible, that has the same consistency strength, as well as +4, +5, so on, up to the next measurable, up to the next measurable limit of measurables. So really quite large. The natural limit is up to the next thing that is +2 strong. It's not clear that we get that by some unfortunate technical limitations, but you do get at least up to the next cardinal that has a lot of measurables below it. Okay. So just for simplicity's sake, we're going to be showing this for a proper class rather than just for a particular successor ordinal. So Apter and Sargsyan show that a hyperstrong cardinal is equiconsistent with having one strong cardinal and everything's degree of strength as weakly indestructible. And you also get that you can have a strong cardinal that's a limit of strong cardinals that are weakly indestructible. And so the consistency of a proper class of weakly indestructible strongs. So a strong reflecting strong cardinal is going to be actually significantly stronger than a hyperstrong. So while this previous result here is saying that you can have a lot of strongs that are weakly indestructible, what my result is saying is that it's actually strictly harder to get a lot of strongs where all the partially strong cardinals have indestructibility for small degrees of strength. Now, strong reflecting strongs are not always not always stronger than a hyperstrong. For the most part, we care about the case when there's a strong above a strong reflecting strongs, because otherwise, if we're strong and there's no strong above you, then being SRS, strong reflecting strongs, is the same as being hyperstrong. But of course, if you have a strong above you, you're much stronger. You actually have a proper class of hyperstrongs below you. Okay, so it's a big jump in the consistency strength. Okay, so what do I mean by weakly indestructible, first of all? Well, I mean that after forcing with anything that's less than or equal to kappa distributive and less than kappa strategically closed, you maintain your, say, row strength. That's what it means for your row strength to be weakly indestructible. Okay, and strategically closed, if you don't know what that means, you can think of it just as closure. It's just a weakening in the sense that you don't have control over the full sequences, just like half of them, and you have the sort of another player clean up your mess at limit stages. Okay, and this statement, UWISS, universal weak indestructibility for small degrees of strength, a bit clumsy, I know, but it's just the statement that you have anything that's +2 strong as weakly indestructible. Okay. A very useful result about strong cardinals that is, I think, often glazed over is this sigma-2 reflection, which basically states that that if something holds in a level of V in the cumulative hierarchy, then you can get it to hold for a level of V below whatever strong you have. And in particular, if you have parameters below that strong, then you can, again, have that hold with those parameters too. And this result is really quite useful. So for instance, if we are strong up to another strong, then you are strong yourself, right? So the proof of this is if you are not strong in some V delta, then sigma-2 reflection tells you that, well, that should hold with some delta that's small, right, below the next strong, and in which case the row witnessing that you're not strong in that will have to be below the next strong. So in that case, you're not strong up to the next strong, okay? So just a kind of neat result, useful. By strong reflecting strongs, I mean that you are lambda strong and you can choose these embeddings such that the two models agree on what is strong below lambda, below your strength. So this is really something that approaches the idea of a wooden cardinal, right? A wooden cardinal says that you have lots of these cardinals that reflect a lot of different subsets. And this is just saying that you're reflecting the set of strongs. Okay. And again, we mostly care about the situation where you're strong reflecting strongs with a strong above you. Because if you're not, you're just the same as hyperstrong, which in some sense means that in the original paper with Abdur Sarkisyan, when they were working with a hyperstrong, in some sense, they were working with a strong reflecting strong the entire time. Okay. So now let's actually turn to the inner model theory part of this. To start proving things, okay? So remember that we're going to be trying to classify consistency strength in the large cardinal hierarchy. And forcing is, again, mostly good for showing results of the form. I have this property relatively consistent to some large cardinal axiom, but largely speaking, it's kind of hard to get the reverse to hold. Okay, But inner models are quite good for this type of inequality. The idea is that we have this property that holds of the wider universe, and then we move to some core model and see what large cardinals exist there. And that's exactly what we're going to be doing here. Okay. So I am going to need to sort of introduce some basic properties of the core model, right? But the main idea is that if we have this universal weak indestructibility for small degrees of strength, then we'll get a bunch of SRS cardinals in the core model from strongs in V. Okay, so in particular, we have that the kappa plus 2 strong cardinals of V will be fully strong in K, while these strong cardinals of V will be SRS in K. And so now I'm going to, give this background on the core model. I'm not going to assume that people know too much about it. Okay, so for the core model below a wooden, we have three main properties we want to talk about. There's local definability, which is just that K up to H kappa can be defined in H kappa. There's generic absoluteness, which is that the core model is going to be the same in any set generic extension of V. And then we have this more complicated result from Schindler using this initial segment condition, which basically says that if you are kappa plus delta strong in V, then you are less than kappa plus delta as calculated in V strong in the core model in the H hierarchy. Okay, so what do I mean by that? Well, if you are, say, kappa plus 2 strong in V, what this says is that you are kappa plus plus, as interpreted in V, strong in K in the H hierarchy. And so you have an embedding from K into some M. It's just that K and M agree on H kappa plus plus, again, as calculated in V. Okay. So there's, I give a proof of this, but I feel like it's kind of technical and may not be worth the time to actually prove it. So let's just get to the main structure of the proof using intermodal theory, which is that we're trying to get SRS cardinals from weak indestructibility. So we assume we have this universal weak indestructibility for small degrees of strength. And then what that means is that we have this sort of immunity to forcing for both the core model and for kappa. And we use that immunity to forcing to show that anything that's plus 2 strong is fully strong in K. And then we show that anything that's fully strong in V is SRS in K. Okay, so let's show that first part, that anything that's plus 2 strong will be fully strong in K. So let's choose something that's sufficiently large that we want to have its strength to be. We can just might as well assume that it's inaccessible just for notation's sake. Okay, now let's collapse lambda plus down to be kappa plus over V to get VG. So this collapsing is going to be less than kappa closed. It's going to be less than or equal to kappa distributive. So it's sort of appropriate for our purposes. What that means is by indestructibility, we're still going to be kappa plus 2 strong in VG. And so what that means is as we calculate kappa plus plus in VG, kappa is going to be less than that strong in the core model of VG in the H hierarchy. Okay, but the core model of VG and V are the same. So kappa still has that strength in the core model of V, where lambda was still inaccessible. So in particular, agreeing on the H hierarchy is going to be the same as agreeing on the V hierarchy up to lambda. So that means that kappa would be lambda strong in K. And as lambda was arbitrarily large, we get the result that kappa was fully strong in K. All right. So now we just need to show that the things that are fully strong in V are SRS in K. So let's start by having this extender that generates this ultra power where we are lambda strong. Okay, now we can do a few things with this extender. We can restrict the embedding JE to K. That'll give us an embedding from K to K as interpreted in the ultra power. We can also restrict down E into K just by intersecting it to get some f. And by that previous Schindler initial segment condition stuff, we can actually show that this f will be on the sequence of k and be an element of k. So what that means is that we can take the ultra power of k by this f and get another version of k, the ultra power of k. And then we can use a factor embedding kf to get this commutative diagram with 3 versions of k. All right, so the goal here is, if we're trying to show that kappa is SRS up to, say, lambda, meaning that it agrees on strongs less than lambda, it's lambda strong and everything, what we want to show is that k and the ultra power of k agree on strongs below lambda. So that's sort of our goal here. So we have this commutative diagram. The critical point of the factor embedding is going to be at least lambda. And so what that means is, just by elementarity, these two models, the ultra power of k and k in the ultra power, are going to agree on strongs less than lambda, okay, just by simple elementarity. So now our goal is to show that k and k in the ultra power agree on strongs less than lambda, because then all of these 3 models will agree on strongs less than lambda. Okay, so that's sort of our goal here. So let's start with that. Well, first of all, local definability tells us that k up to lambda is the same as k in the ultra power up to lambda. Remember, lambda is strong here. Okay. So what that means is that they agree on what is less than lambda strong. Okay. But what we're going to be showing is that those cardinals are strong. Okay. So okay. Those cardinals are strong. So the idea is, okay, because lambda is V strong, what that means is it's a limit of things that are +2 strong. So it's in particular a limit of k strong cardinals. And similarly, a limit of k in the ultra power strong cardinals. Okay. But being strong up to the next strong means that you are strong. So if you are less than lambda, your next strong is also less than lambda. So if you're less than lambda strong, you are less than the next strong, so you're fully strong. So again, all that is just to say, being less than lambda strong means that you are fully strong in both k and k in the ultra power. Okay, well then that means that k and k in the ultra power agree on strongs less than lambda. K in the ultra power and the ultra power of k agree on strongs less than lambda by elementarity. So that means that k and the ultra power of k agree on strongs less than lambda. And so finally, f is therefore reflecting strongs as an extender. So kappa would be strong reflecting strongs in k. Phew, okay. So all that is just to say that we now have a lower bound on the consistency strength of having a proper class of strongs with universal weak indestructibility for small degrees of strength. Namely, you need a proper class of SRS cardinals. Okay, so for the other direction, we're going to be using forcing, kind of as expected. And the idea is really just to force a lot, and hopefully these SRS cardinals end up being strongs on the other side. And so this is really what the theorem is going to be saying. Okay, so what's the idea behind the forcing? Well, we're going to be using a fairly standard trial by fire idea. So the idea is, if I want to find something that's indestructible from, say, my axe, then I'm just going to axe everything I possibly can until I find something that my axe doesn't destroy, in which case, voila, I found something that's indestructible by my axe. So I just do that with every cardinal, and then I move on to the next cardinal, hitting it as much as possible, destroying as much. Okay, so sort of whatever remains should be weakly indestructible in the end. Now, this is sort of the idea, but this raises 2 questions. For one thing, how do we know that we're left with anything in the end, right? If I'm just hacking away at stuff with my axe, how do I know that I haven't just killed everything with it? And secondly, we're supposed to be getting a bunch of strong cardinals in the end. But we also had this previous result that told us that we can't have two strong cardinals while everything is weakly indestructible, right? So in the end, we are indeed going to get that these strong reflecting strongs will be strong in the end. But what does that mean for the previous observation that anything that was left should have been indestructible? Well, the idea is that we did in fact destroy these cardinal strength, but we also resurrected it later. And so these resurrected degrees may not be indestructible anymore. They will be destructible. But the small degrees of strength that we didn't destroy remain indestructible. Okay, so that's sort of the idea there. The main issue here is interaction with things. So these cardinals are not going through this trial by fire alone. It may be that you destroy strength, but later on, another cardinal comes along and acts as sort of a medic and is able to resurrect some previous degrees of strength. So the sort of picture here is we have this kappa. It has a strength up to here, say. And then at stage kappa, we destroy some of its strength. And then the next stage of forcing delta maybe occurs lower than that. And because its forcing at stage delta is relatively large, it can affect all that stuff bigger than delta and might resurrect some of those degrees of strength. In which case, well, we never tried to destroy those strengths again, so they might be destructible still. That's sort of the idea. But this isn't really an issue if we're only talking about small degrees of strength. So if I have this kappa and I destroy stuff much further down, then my forcing at stage delta can't affect things below delta. So in particular, it can't resurrect any of these smaller degrees of strength. And so the lack of those degrees of strength continues on. Okay. So it's fairly straightforward, I think, to at least believe that this forcing will yield weak indestructibility for everything's +2 degrees of strength. Okay. So how do we get Strongsian, right? What's the sort of point of these strong reflecting strongs? Well, the idea is that we want V and M to agree on the forcing up to stage lambda. Okay. And the way that happens is, well, we want J of P lambda to be the same as P lambda, followed by some tail forcing. And what's going to happen is we're going to try to generate a generic for the tail forcing from 1 over P lambda. And then that'll allow us to lift up, of course, okay, to this J plus, but this J plus need no longer reflect strongs like J would. Okay. And so the general idea is that these SRS cardinals are in the end going to be lambda strong after forcing with P lambda. So you can think of that as saying that by stage lambda, we will have resurrected their lambda strength until they'll end up being strong in the end. Okay, now some notation that I'm going to be using here that I sort of introduced a little bit before, but I might as well reiterate now. So I'm going to represent the next measurable by kappa plus sharp. The next thing that is +2 strong by kappa plus sharp sharp. The next thing that is strong by kappa plus pistol. And these are the things that I've sort of already talked about or written down. An arbitrary generic extension I just use with VP, and by, say, M mid kappa, I just mean the kappath level of the cumulative hierarchy of M. So V kappa as interpreted in M. Okay, so let's actually get into some of these details. What we're going to want to be looking at is certain kinds of posets. I'm just going to call them appropriate. So by those posets, I mean things that are strategically closed, have the right amount of distributivity, and that destroy the row strength of delta. Okay, so being weakly indestructible means that you don't have these posets around. And a nice sort of lemma here is just that we can bound our search for these posets. So we don't need to look super far. We can just look up to the next strong cardinal in rank. So we can actually prove this relatively easily just with sigma 2 reflection. So if we have something that is appropriate, that'll be true in some sufficiently large v up to lambda. And then using sigma 2 reflection, we can make sure that this lambda and thus this rho star star and everything can be less than the next strong delta plus pistol. Okay, and that just easily tells us that we can bound our search. And this is, again, something that was very similar to Apter Sargson's original paper. Okay, so let's actually define the preparation because it gets a little hairy. So first of all, we're just going to begin by adding a Cohen subset of omega, just to use gap forcing things. So we don't need to worry about having accidentally added new large cardinals or anything. Okay, we're going to be using an Easton support, or sometimes called reverse Easton support iteration, where at stage delta, what we do is trivial unless we're inaccessible. And if you have weakly indestructible strength at stage delta, then you're also trivial. And otherwise, what we do is we force with a lottery sum of two things, B star C. And what B is it first, it's delta rho appropriate, so it destroys the rho strength for the minimal rho. And C is a collapsing poset that makes sure that if B is too large, then we just collapse it down. Okay, and here's the sort of technical specifics about what that is. But all that is really kind of a bit too technical to really take in, I think. So the idea is that we're only going to be forcing at stages that are +2 strong. If we can destroy strength, we do, and we do so using posets of small rank, meaning less than the next strong. And then we collapse them down to be small in cardinality. And the reason why is just to give us control over the tail forcing. So in particular, if we do some forcing at stage delta, then what comes before us should have been delta CC. And the reason why is if I have some delta here, and I had some kappa where the stage of forcing reaches above delta because it's so large as a poset, then we would have collapsed down this such that we wouldn't have done any forcing on at stage delta. Okay. And so this allows us to make use of the tail forcing being strategically closed and distributive. Okay. And so we can make use of it when we're talking about appropriate posets. Okay, so we can pretty easily establish universal weak indestructibility for these small degrees of strength. So if I have something that's rho strong for some small rho, then at stage kappa +1, my degrees of strength are already going to be indestructible, my small degrees of strength. So what this tells us is that my degrees of strength up to kappa plus sharp sharp is going to be indestructible in the end. But what kappa plus sharp sharp is might change. So this is sort of an unfortunate little limitation, I guess. So the proof sketch of this is that because my rho is small, the tail forcing, the next stage of forcing, occurs way after it. Okay. So in particular, kappa will still be rho strong in the end. So if I had something that was appropriate in the end, kappa rho appropriate, then what I can do is, well, it's going to appear at some stage lambda, in which case I can consider the tail forcing from kappa to lambda star q, and that'll be kappa rho appropriate at stage kappa. But q kappa was already supposed to destroy as much strength as possible. So there's no way that we could have this rho be smaller than what was already destroyed. Okay, so that's sort of a contradiction, and so we have these weakly indestructible degrees. Okay, so if we have, say, a proper class of strongs, we can define what this poset is, because we can bound what we're searching for, and this will force UWISS. And in fact, it'll force that we have weakly indestructible strength up to kappa plus sharp sharp as interpreted in VP kappa +1. Okay, and we can prove this pretty easily. So first of all, any measurable is weakly indestructible. I guess I didn't mention this before, but the proof of this is really quite simple, because if you're weakly indestructible, right, what posets are appropriate for that? Well, it's the ones that are less than or equal to kappa distributive. So they're not adding subsets of kappa. So whatever measure you had in the ground model is still going to be a measure in the generic extension. Okay. If you are +2 strong in the end, that means you're going to be +2 strong at stage kappa +1. And we already knew that its strength there is going to be indestructible. So we're done. We know that we have universal weak indestructibility for strong degrees of strength. But then the question is, how do we get strongs, right? Okay, so they're definitely coming from lifting embeddings, right? But the issue is partly that we're going to be doing a lot of forcing, right? So if we have a lot of strongs, then we're going to have a lot of things that are, +100 strong. Each of those is got a limit of things that are +99 strong, and so on and so forth. So we're going to have a lot of +2 strong cardinals. Okay. We do so much forcing that in the end, what we really want is that J of P and P are going to have to agree on a large initial segment, basically to make sure that we don't accidentally screw things up on the M side and do some forcing that we don't want. But making sure that that happens means knowing what P is like. And that requires knowing these bounds on the ranks of appropriate posets. And the bounds that we use were strongs. So we should have that M and V should agree on strongs. And in fact, we have that. If these two things agree on strongs, then P lambda is going to be the same in both, assuming that lambda is a limit of strongs. Yeah. Okay. So now we can actually have the main lemma here, which is that if you are lambda SRS, meaning lambda strong, reflecting strongs, then P lambda will force that kappa is lambda strong. So we will have destroyed its strength, but resurrected it by stage lambda. Okay, so proving this takes a while, so it's going to be a fair amount of time. So we start with a lambda SRS embedding, where without loss of generality, lambda is non-measurable. So we don't really do any forcing at stage lambda. If we take P lambda and apply J to it, we get P lambda of V, right? We just showed that V and M interpret P lambda the same way, followed by the tail forcing from lambda to J of kappa, and then from J of kappa to J of lambda. Okay, and we're breaking it up that way because we can break up P lambda as P kappa, followed by the tail forcing from kappa to lambda. So we have this generic G as G0 star G1, generic over that. Now, if we look at J image of G0, right? Because in the end, what we're going to want is that J image of G is going to be contained in some H, right? So first of all, what is J image of G0? Well, it's basically just going to be G0, right? Because the supports of things in P kappa have bounded support, right? They're up to some alpha less than kappa, right? So if I apply J to that, it's really just going to be the same thing, but now just appended with a bunch of ones at the end. So J image of G0 has trivial conditions between kappa and J of kappa. Okay. So in particular, it's not going to affect anything over here on this middle sort of tail forcing. And also, it's not going to affect G1, right? Which is nice. So what that means is that any generic that we get for this middle forcing is going to be compatible with J image of G. And for this latter part, the generic that we're going to get there is just going to be generated by J image of G1. So it's going to be compatible with that too. Okay, so let's actually show this. We can regard M without loss of generality just as an extender embedding, so we can represent it in this way. We can choose particular representatives for P kappa in the tail forcing after kappa. And we can consider this kind of hull that allows us to range over all of these functions, but where we are evaluating at specific inputs here. And what that tells us is that we're actually going to be closed under kappa sequences too, because if you have a sequence here, you just consider the sequence of representatives, apply J to that, and you don't need to worry about what choice of inputs you have here. It's all just the same input. So N is going to be contained or closed under kappa sequences. Okay. The point here is that, well, okay, maybe we don't know how to get a generic over mg, but we can at least get one over ng. Okay, so we can build one in a sort of standard way, right? So this tail forcing is going to be lambda plus strategically closed in mg and ng, but because we have enough closure in V of these sets, that gives us kappa plus strategic closure in V, okay? We can count the number of dense sets of Ng. There's only going to be kappa plus many, and that means that we can just one by one intersect these dense sets, or one by one extend into these dense sets, and that'll allow us to form a generic over Ng. Okay, in the standard sort of way. Okay, but we can actually show that this H0 is not only generic over Ng, it's actually going to be generic over the entire thing we wanted, Mg. Okay, so the way that we show that is we have some random open dense set. We can represent it as J of f of r. And so we can consider an Mg J of f, but evaluated at all of these different r's. Okay, all of these different r's. This is going to have size lambda. So that's a bit too much for V to intersect and know that it's open dense, but Mg knows that its tail forcing is lambda plus strategically closed. And so it's going to be less than or equal to lambda distributive. So it can intersect all of these dense sets. Okay, so we can consider this E, that's the intersection of all of those. But this E is going to be an Ng, right? We can represent it in this sort of way. And so what that means is that E intersect H0 is going to be non-empty, but that's contained in D intersect H0. So we have a non-empty intersection with D. So it tells us that H0 should actually be generic over Mg. Okay, so now we have G, we have H0. This is going to be generic up to J of kappa in M. And now we just need to worry about the tail from J of kappa to J of lambda. Okay, so the filter generated by G1, J image of G1, remember that G1 is contained in the tail from kappa to lambda, so J image of G1 is going to be contained in the tail from J of kappa to J of lambda. And we can show that this filter is going to be generic. Okay, so again, we can represent these dense sets by, say, J of D of R. The tail forcing in VG is going to be less than or equal to kappa distributive. So this is partially why we need to consider weak indestructibility so that we can have this distributivity of the tail post set. Okay, but nevertheless, we can intersect all these kappa many dense sets. This is going to intersect G1 because G1 is generic. So what that means is we have some P in G1 that intersects D of S for every S. And there's going to be some Q in G0 that forces this. So by applying J, in M, we know that J of Q forces that J of P is in J of D of S for every S. In particular, J of Q is going to force that J of P is in D. And so what we have is that, well, because J of Q is just Q, Q is going to force that J of P works. So J image of G1 will work as the filter, as the generic filter. Okay. So we have H1 now, and it follows that J image of G0 star G1 is going to be contained in G1 star G0 star H0 star H1. And that's because, again, J image of G0 doesn't affect anything between kappa and J of kappa. In fact, it's also not going to affect anything above J of kappa either, again, because its support is so bounded. J image of G1 generates H1. And so what that means is that we can lift to J plus. And this J plus will still be lambda strong. Why? Well, because H0 star H1 don't add any subsets of rank less than lambda. G is basically contained in lambda, so they'll agree on the less than lambda rank sets. Okay. So we've built this thing in VG. We know that kappa is going to be lambda strong there. Whew, okay. So really what we've shown is that if we have something that's lambda SRS, then we can lift in P lambda. So if you're SRS, then you will be strong at the end. And that's where we get this other half of the theorem, that P will force that there's a proper class of strongs if we have a proper class of SRS cardinals. Okay, so that's sort of the main result here about looking at small degrees of strength and getting that from reflecting strongs. But we can actually expand these results to get more reflection in the end. So I remarked before that we started out with these SRS embeddings, but this J plus that we lift to may not reflect strongs anymore. But we can actually get that it will reflect strongs if we reflect the appropriate name in the beginning. So in particular, if we have something that is lambda strong reflecting strongs and a certain name for a given subset of some, subset of delta in the generic extension, then in the end, kappa would reflect A. So if you want to reflect strongs in the end, you need to, in the ground model, reflect strongs and the name for strongs. Okay, and so a corollary of this is that if you are wooden and you just continue your preparation all the way through, you're still going to remain wooden. So this preparation will preserve wooden cardinals. Okay, but what other limits can there be to reflection here? Well, we can consider, say, this cardinal idea of a wooden by weak indestructibility. So what that means is you kind of consider something where every subset of delta has a cardinal that is less than delta strong reflecting A that has its strength and reflection weakly indestructible. Okay. However, such cardinals cannot exist. You cannot have indestructible reflection properties all the time. Okay. And the proof of this isn't super difficult. If we consider the set of ground model weakly indestructible strongs, or less than delta strongs, we can consider something that supposedly reflects that. Okay, we can add a Cohen subset of kappa plus and consider an arbitrarily strong J from VA to MJ of A. And the next less than delta strong cardinal, kappa prime, in the set of weakly indestructible things will be destroyed in VA because this is some small forcing. It'll be destroyed, sorry, by adding a subset of the successor cardinal. Okay, because A is from a small forcing. Okay, but then reflected to the V side, what that means is that some mu less than kappa was destroyed by Cohen forcing destroyed by Cohen forcing by adding a subset of the successor cardinal. So in V, it was destroyed by adding a subset of kappa plus and then a subset of mu plus. But then that would contradict that they were W in the set of ground model weakly indestructible strongs. Okay, so what this means is that there's really a limit to the amount of indestructible reflection properties that you can have. In particular, you can't have indestructible reflection properties for the property of reflecting, or for the property of being weakly indestructible. Sorry. Okay. But nevertheless, there is still this case where woodens can have every less than delta strong cardinal belief them weakly indestructible. So what that means is basically you can have all of their strengths weakly indestructible, but just not their reflection properties. Okay. And so we actually have this equiconsistency then. If you have a wooden cardinal, you could also have it where everything below that has weakly indestructible strength for small degrees of strength. And you could have it so where all the strong cardinals are weakly indestructible. Okay. So I mentioned earlier that there was this dichotomy between having the small degrees of strength and the large degrees of strength indestructible, where the small degrees were ironically harder to get. They were a stronger consistency strength than for the larger degrees. But this actually tells us that if we have enough strongs, that actually levels out and it'll be equiconsistent with a wooden cardinal. Okay. Now the proof of this is actually quite simple. We have the second one just by continuing our previous preparation for the small degrees. For the large degrees, we're just going to be forcing at strong cardinals. And what we do is we just destroy as much strength as possible at those strong cardinals, or really at the less than delta strong cardinals. And we can lift by the same idea as possible, or same idea as before, to get that we can, find these names, and that'll allow us to get the appropriate reflection properties for delta. And we don't have to worry about this idea of like resurrecting degrees of strength or anything like that, because there's not going to be any interaction between the stages of forcing, right? So if you destroy a degree of strength, it's necessarily going to be below the next stage of forcing, because we're only really forcing at the strong cardinals of V up to delta. Okay. And just as a sort of last note, we can also do all of this work with supercompact cardinals, right? So if we have supercompacts reflecting supercompacts, that means that in the end, we'll get a bunch of supercompacts and the kappa plus supercompactness as weakly indestructible. And this is by less than kappa directed closed posets instead of less than kappa strategically closed. This is actually quite easier than with strongs, partly because we're using the directed closed posets, which are nicer than the strategically closed. So they allow us to use just a really easy and nice master condition argument, as opposed to using like this whole argument and then, trying to finagle that around a bit. But we don't get an equiconsistency like for the strongs because we needed core model theory and inner model theory, and supercompacts don't like play nicely for now anyway. So we don't have an equiconsistency like that, but we do at least get the same sort of equiconsistency for wooden for supercompact cardinals. Okay. And yeah, that's the end of my talk.
Are there any questions for our speaker? Well, if there are no questions for James, then let's thank him again.
Thanks a lot.
And of course, thanks for having me and everything.
Thanks, James.
Yes, thank you.